All right, so this is a joint work with a lot of amazing co-authors with Sampath, Michael, Jamie, Mallesh, Aaron, and Ricky. Most of us are from Penn. Mallesh is an econ faculty at Rice. Our stellar postdoc, Jamie Morgenstern, is joining Georgia Tech. I myself will be joining Microsoft Research in Minnesota in the near term. So in this paper, we study a pretty interesting trade-off between learning incentives and fairness. Different one. The kind of motivating examples we think about is the recent peer-to-peer platforms such as Airbnb and Prosper that allow users to provide short-stay housing and landing services to individuals. Okay? So here we think of these users on these platforms as myopic agents because they're primarily concerned about the rewards or experience that immediately collected by selecting or providing these services. Okay? And there is some recent evidence showing that some of the users in these platforms can have unfair discrimination or unfair bias against some of the subgroups of the population. Okay? While there may be many potential reasons to induce such unfairness, the main friction of unfairness we study in this paper is myopia. Okay? For example, it is shown that some of the Airbnb landlords with no prior exposure to some of the minority renters were more likely to discriminate such minority. Okay? And because they may never provide services to these minority, they may never have a chance to correct their bias. Okay? And the high-level question we after in this paper is that can we have a principle that creates fairness incentives for these myopic agents? While the myopic agents are making the decision themselves, can a principle create economic incentives so that the agents can behave in a fair manner? Okay? Along with this, we'll also think about an interesting technical question is how much information does the principle need in order to incentivize fairness in this case? Okay? So we're going to study this problem under the formulation of this so-called contextual bandit learning setting. Okay, so we're going to represent this k different subgroups of the population as k different arms. And in each round in the learning, over a time horizon of t rounds, individuals show up for each group, okay, along with their context. You can think of the context for each individual as their feature or their profile on these kind of platforms. The agent will select an individual among these k individuals and will generate a reward for selecting this individual. Okay, so here we'll assume a linear reward function, which means the expected reward for selecting any individual is an inner product between unknown vector theta j and the context vector of the individual. Okay, I just want to tell you a very important special case that's even more studied in the literature is the classical stochastic bandit setting, where the contexts are just the same for everybody. The reward is just simply described by a single number, which is the mean reward of the arm. Okay? So how does the interaction between the agent and the principal take place? Okay? So each round, there's a myopic agent that show up, and he got to observe all the historical data on the platform, okay? Such as the decisions made by the previous agents, and all the contexts that have shown up so far, and all the rewards that have been generated. Okay? And there's a principle, okay, he really cares about fairness. He tells the agent, hey, if you actually play individual I will pay you extra bonus of PI, okay? In particular, this principle happened to be a computer scientist, so the payment could be generated under some randomized scheme, right? And given the payment on these individuals, the myopic agent will make such decision that is try to maximize the empirical estimated reward of the individual plus the principal's payment. Okay? And the principal's goal is simply to minimize the so-called cumulative regret, subject this to some form of fairness constraint. Okay? So let me quickly tell you what these two things are. Okay? So cumulative regret is a very simple thing. In English, it just means this is the difference between the best achievable expected reward minus the expected reward achieved by the algorithm. Basically, how much better you could have done in hindsight. Okay? And in In the standard literature of online learning, we say that algorithm has no regret if the cumulative regret is sublinear in the time horizon t. Okay, and usually we can achieve square root of t of cumulative regret. Okay, this is just standard things. More interestingly, we want to learn under some form of fairness constraint. So if you've been to Michael Kearns' talk yesterday, you may have already seen plenty of that. So the fairness constraint we consider here is this kind of meritocratic fairness constraint. Okay, so in English it says, I'm allowed to play an arm j with higher probability than arm j prime, only if j has higher expected reward than j prime. Okay, in other words, I'm allowed to favor arm j only when I know j has higher expected reward than j prime. Okay? So I'm not going to repeat the formal definition, but I would like to highlight two technical points about this definition. There are two obvious algorithms that satisfy this definition. The first one is just uniformly randomly play among all the arms. Okay, so this is fair. And it's pretty nice because it allows for exploration for the data. So we can always play all the arms together. Okay? The second algorithm that satisfies this fairness condition is to just deterministically select the arm with the highest expected reward. Okay? So this is also pretty nice because it's compatible with optimality. If the principal collect enough data and learn enough from the data, asymptotically, this will give no regret. The question is, how do we learn in a fair manner? Okay? So we studied this problem under two different informational models. The first one, we call it the full information model. The principal here get to observe everything the agent get to see. Basically, the context, the decisions made by the agents, and also the realized reward generated so far. Okay? So here you can think about the principal is simply someone that monitors the platform itself. A more interesting model is the so-called partial information model. Okay? So here the model is more stringent. The principal only get to observe the decisions made by the agents. Okay? Not the context, not the realized rewards. Okay? So here you can think about the principal as some kind of external regulator. And for reasons such as privacy, the principal cannot open the book of the platform and see historical data. But he still want to incentivize fairness in this case. All right? Okay, so we want to optimize our regret subject to fairness constraint under these two different models. And here's a quick snapshot of all our results. So as we expected, things are much easier under the full information model. In both the classical bandits and linear contextual bandits setting, there are some really nice payment scheme that guarantee fairness in every round and sublinear regret and sublinear cost in total. Okay? But things get more interesting under the partial information setting. Okay, so first we can show that if we want to guarantee, in the classical bandit setting, if you want to guarantee fairness in every round, actually there's no way you can do better than linear payment over time. Okay? But if you allow some small room for mistake, if you allow for some small number of unfair rounds, actually you can recover the same regret or same cost bound as in the full information setting. Okay? But in the linear contextual bandit setting, things are strongly negative. There's basically nothing we can do much. We cannot achieve sublinear cost and sublinear number of unfair rounds. Okay, so in this talk, I would like to mostly focus on the positive results in the classical bandit setting. Hopefully some of the ideas can translate to other settings as well. The key technique I want to highlight, which you may have already seen in yesterday's talk, is the idea of confidence interval chaining. And I also want to talk about how to do that under this more stringent information model, the partial information model. Okay? So what's confidence interval chaining? Okay? So at any point in the learning or the games, you can maintain a confidence interval on the reward of each arm. Okay? So in the middle of each confidence interval, you get the empirical estimate of the reward of the arm. Okay? And the length or the width of the interval basically scale with 1 over square root n, where n is the number of times the arm is played. Okay? This is very standard. Okay? If you don't care about fairness or absent fairness constraint, a very standard algorithm to achieve no regret would just play the top arm with the highest upper confidence interval. Okay, this case is the arm 1. Okay, but this will violate fairness constraint. Instead, a previous paper by Joseph et al. In last year's NIPS showed that the fair algorithm will actually play uniformly at random from the chain set. So what is the chain set? The chain set is the set of arms that has confidence interval chained to the arm with the highest upper confidence interval bound. Okay, so the intuition that we need to do that because we don't have sufficient data to fully determine the relative ranking of all of these arms. Okay, so we need to play uniformly at random. All right, so the myopic agents are actually the ones who select the arms. The principal only get to offer a payment. So how do we incentivize the agent to play this fair UCB algorithm? Okay. Actually, under the full information setting, this is very, very simple. The way you do it is simply select an arm, J, uniformly at random from the chain set, and then offer payment that is the maximum empirical reward minus the empirical reward for this arm, and offer payment 0 for everything else. Okay? So just by doing that, you can induce a uniform distribution among the chain set. All right? And the principal can offer to do that because he gets to see everything, you get to see the empirical reward. Things get more interesting when you have less information. So in the partial information setting, you never get to see the realized rewards. And because of that, you don't actually have the empirical estimate for the rewards. Okay? However, there's still some important piece of information the principal gets to have. The principal does know the length of the confidence interval, or the width, because it's only a function of the number of times each arm is played. Okay? The key question is, with just this limited amount of information, can we still identify the chain set? You know? Okay, so the key idea here is to introduce a different set, what we call the active set. Okay, so what is the active set here? An active set is basically a superset of the chain set, and it's also guaranteed to have higher reward than the rest of the arms not in the active set. Okay, and to do that, to satisfy this property trivially, we can just initialize the active set to be the set of all arms. Okay, and the algorithm would do the following. It would try to select an arm uniformly at random from this active set, and offer payment that is basically the size of the active set times the largest confidence interval in that set. Okay? And offer payment 0 for the arm that's not selected. Okay? My claim is that if the payment is large enough, okay, so whenever a principal selects an arm, he can always incentivize the agent to play it. This is a fair scheme because it's really playing uniformly at random among the active set. However, a problem arises if the payment is not large enough. Okay? In particular, if there's an arm we know has really low reward, maybe the principal will not be able to incentivize the agent to play it. Okay? So this is a picture that describes the situation. In particular, if the principal select arm 4 and pay the sum of the confidence intervals for the agent to play it, the agent would not play it. It would instead play arm 1, which has the highest empirical reward. Okay? And because of that, we're inducing a non-uniform distribution among the active set. And this will incur unfairness. But the claim is that maybe this is not so bad. Whenever this situation arises, the principal can detect it very quickly because it's aiming to induce a uniform distribution among these at most k arms. It only takes around linear in k rounds. The principal can detect whether this has arises with high probability. Okay, so this will incur some small number of unfair rounds, so maybe it's not a big deal. The problem is how do we keep maintaining a true active set? Okay, so here we need to update our active set whenever the principal detects some arm have really low reward in this case. Okay, the way we detect the active set, sorry about the animation, but the first step is to first pay 0 payment for every arm in the old active set. This will allow you to identify the arm with the highest empirical reward, okay? Just by the myopia of the agent. Now we will include arm 1 in the active set because we know it's the highest empirical reward. Next, we will offer payment 0 for the arm 1 and raise the payment for all the other arms to be 2 times the largest confidence intervals in the set, okay? And that will allow us to identify arm 2, which has the second highest empirical reward in the set, okay? By doing a similar thing, setting payment to be 0 for arm 1 and arm 2, and raise the payment for the other arms to be 4 times the confidence interval, we can identify the third highest empirical reward arm. Okay, we can do this sequentially until the Myopic agent would not stop playing a new arm. We know we have identified a new active set. And this active set will be guaranteed to be at least 1 smaller. Okay, we have reduced the size of the active set. Okay. To wrap up, this is basically the algorithm under the partial information setting. So we basically alternate between 2 subroutines. The first subroutine, we try to incentivize the agent to play uniformly at random among the active set. But sometimes we may have failed to incentivize the agent to play it. And whenever that happens, we'll try to update the active set. And whenever we update the active set, we shrink the active set by at least 1. Okay, so we only update the active set by at most k times. Okay, and for each update, we will incur about linear in k number of unfair rounds. So in total, we'll only incur k squared number of unfair rounds. Okay, and at the same time, the algorithm can achieve square root k cubed times t regret and cost. Okay, this is basically the upshot. Okay. In the end, I would like to highlight an open question. There are some open questions we left in the paper. This is the one I myself find the most interesting technically. So the contextual bandit setting under the partial information model seems like a very dark corner to us because we have no positive result at all. So I'm very curious whether we can get some positive results by thinking a slight variant of our model. In particular, our lower current lower bound holds for adversarial contest arrivals, which is a very hard setting to operate. My question is, can we design possible positive algorithm when the contests are drawn from stochastically from an unknown distribution? Okay. Let me know if you know how to solve a problem. And that's it. Thank you.